This video discusses related rates. When we say related rates, we are going to look at the differentiation with respect to time t. That's why we have the term rates. We are going to look at related rates because in this section you are going to see at least two related variables, sometimes three related variables. We will first write down an equation depicting the relationship between those related variables, and then we will differentiate that entire equation with respect to time. Before all these guidelines, I have to mention you something regarding this section. All the questions from this section are word problems. Some people hate word problems. However, the word problems in mathematics are always significantly easier compared to any other technical mathematical problem if you read that problem carefully. Only challenging part of a word problem is reading and understanding the given problem. So, the first and the foremost important thing when doing a question from this section is your patience. You must read the question thoroughly. Understand the practical configuration explained in the problem. After that, you will need to draw a figure. Once these two steps are completed, we can start working on this problem. The very first step is to write down the relationship as an equation. Once you finish writing down the relationship as an equation, we go on to step number 2. In the second step, we will identify the variables and the constants in that equation. That step is very important. Say for example, I have to differentiate d by dt, because we are going to differentiate with respect to time in this case, something like a times b. If a is a constant and b is a variable, we will write this as a times db over dt. In case if a is a variable and b is a constant, we take the b out and differentiate a. On the other hand, if both a and b are variables, in that case we will write this as a times db by dt plus b times dA by dt. That's the application of the product rule. Likewise, in order to do the differentiation correctly, we must know what are the variables and what are the constants. Once you clearly know what are the variables and what are the constants in that equation, we will differentiate that entire equation with respect to time t. That's our third step. Alright, now we are all set to look at an example. Here's your first example. Let's say we have a cylindrical tank. We're going to pump water into that cylindrical tank. Water is pumped into a cylindrical tank whose base radius is equal to r. Part A of this problem is obtain an equation for water volume when the height of water is equal to h. So before working on anything of this problem, we need to read this question carefully, and then we can draw a diagram, and then we can do the differentiation. Water is pumped into a cylindrical tank whose base radius is equal to r. So let's go ahead and draw a cylinder. The base radius is equal to r. Let's say this is that base of the tank. Let's assume that this is our tank. We're going to pump water into this tank. Once you pump water, the water level will increase. Let's say the water level is somewhere here. This is all water. Now we will show the given information. Radius is given as r. So let me show the radius of that cylindrical tank. Let's say this is r. We need to obtain an equation for the water volume when the height of water is equal to h. So let me show the height of the water. This height right here is equal to h. How do you write down an equation for the volume of water? Let's say the volume right here is equal to V. Very clearly, V is equal to base area times the height. Since the radius is equal to r, the base area is pi r squared. Height is equal to h. Once you have written down that relationship between the variables that are related, in the next step, you need to identify the variables and the constants. So in this equation, what can you say about V? Of course, V is a variable because as time goes on, the volume increases when you keep pumping water. So volume V is a variable of time. How about pi? Pi is a specific numerical value. Therefore, it's a constant. How about the radius? Well, of course, it is the radius of this tank. Radius is a constant. How about h? H is the height of the water level. When you keep pumping water, h should increase. Therefore, we should identify that h is a variable of time. Let me go ahead and highlight the equation that we have written down. Here is part B of that problem. Differentiate your equation with respect to time. So the equation we have is V equals pi r squared h. Once you differentiate this equation, both sides with respect to time, V is a first order, h is also a first order, and therefore the differentiation is very straightforward. Remember, if I had to differentiate y with respect to x, it was just dy by dx. So likewise, if I have to differentiate v with respect to t, it will be just dv by dt. We know pi r squared, that quantity is a constant. Therefore, it can be factored out according to the second property of differentiation. And then I need to differentiate h with respect to time. Once again, h is a first order variable. Therefore, it will be just dh over dt. That's it. Part C of this problem is, if water is pumped at 50 cubic feet per minute, find the rate of change of height if the radius r is equal to 5 feet. All you have to do is just look at this equation and substitute the given values. What is this 50 given right here? That is the rate where the water is pumped, which means that 50 should be dv by dt. That's given in cubic feet per minute. Then we have pi r squared. R is given as 5 feet. So that should be times 5 squared, that times dh by dt. So we can easily simplify this equation. 5 squared is 25. 50 divided by 25 is 2. I need to divide both sides by pi also. Then we can subject dh by dt. That should be equal to 2 over pi. The units are going to be feet per minute. That's the answer for this problem. Here's your example number 2. Water is pumped into an inverted conical water tank at a constant rate. Part A, obtain an equation for water volume when the height of water is h and radius is r. Let's look at this problem again. Water is pumped into an inverted conical shaped water tank at a constant rate. So first we will go ahead and draw a tank. Let's say this is that tank and water is pumped into that tank like this. Once you pump water, obviously the water level will increase. Let's say the water level is somewhere here. All of this is water. You can see that the given information on height and the radius, they both should be variables. Height of water. Let me show the height of water. That height is given as h. And then we need to show the radius. So the radius is that. Now I need to write down an equation for the water volume. So who can remember the equation for the volume of a cone? Volume of a cone is given by V equals a third pi r squared h. Now I need to identify the variables and constants. What can you say about the volume V? Volume V is clearly a variable. That's a variable of t. Of course, 1/3 is a constant. Pi is also a constant. So all of this part is a constant. How about r squared? Of course, as the water level increases, the radius also increases. Therefore, r is a variable of time t. What can you say about h? H also increases as you keep on pumping water. Therefore, h should also be a variable of time t. Now we are done with that first part. Let me go ahead and highlight the equation obtained. And in that equation, we know what are the constants and what are the variables. Let's go on to part B. Differentiate with respect to time t. The equation we have is V equals a third pi r squared h. When we differentiate with respect to time, on the left hand side, it is just a first order variable. So let me just write it down as dv by dt. On the right hand side, a third times pi is a constant, which I will factor out, just pi over 3. Let me open brackets, and now I need to differentiate r squared times h. You have to apply the knowledge from all the differentiation properties and also implicit differentiation. Since r and h are both variables, when you differentiate r squared h, you have to follow the product rule, because r squared times h is what you have to differentiate. So what is the product rule again? The product rule is, if you have a product of two functions such as f times g to be differentiated, this is going to be equal to f g prime plus f prime g, where f prime and g prime are the first derivatives of f and g respectively. Now I'm going to go ahead and differentiate. I will assume that r squared is my f and h is my g. First, I just need to go ahead and write down f as it is. F is just r squared, and then h should be differentiated with respect to time. What is it? That should be dh by dt. That plus f prime times g. Of course, g is just h. That times the derivative of r squared. How do you differentiate r squared with respect to time t? Basically, what I need is d by dt r squared. This is where we are going to use implicit differentiation, or in other words, simply the chain rule. We can first differentiate that r squared with respect to r itself, and then we will need to multiply that by dr by dt. We saw this in implicit differentiation, and also we have seen this under chain rule. So this first part, r squared differentiated with respect to r itself, is just 2r. That times we need to write down the term dr by dt. That's the complete differentiation with respect to time t. Now we can do some further simplifications if interested, because you can see that r can be factored out. There's nothing much that can be done actually, but let me go ahead and just factor out the r. We have dv by dt equals pi r over 3 brackets r times dh by dt plus 2 times h times dr by dt. Please note that I have factored out 1r. This is basically all I need for part B. Now we can go on to part C. Here's your part C. If water is pumped at 50 cubic feet per minute, find the rate of change of height. If the rate of change of radius is 2 feet per minute, r equals 1 foot and h equals 2.5 feet. Now we simply have to use the equation that we derived early and find the rate of change of height. Rate of change of height is dh by dt. We need to find the quantity right here. Other things are given. We are given the information that the water is pumped at 50 cubic feet per minute. That quantity should be equal to dv by dt. We need to find the rate of change of height. If the rate of change of radius is 2 feet per minute, this is dr by dt, rate of change of radius, and r is equal to 1, h is equal to 2.5. We will simply go ahead and substitute these values in that equation. dv by dt is equal to 50. That should be equal to pi r over 3. Pi times the radius is given as 1 over 3. Brackets r times, which is just 1 times dh by dt plus 2 times h is equal to 2.5 times dr by dt, which is equal to 2. Close brackets. You simply have to solve this equation and subject dh by dt. You can see that this part is simplified to become a 10. Therefore, we can write down that this 3 times 50 is going to be 150, and I will divide both sides by pi. Then on the left hand side I will have 150 over pi, and then this quantity should be subtracted. That is going to be this thing minus 10. That should be the value of dh by dt. If you like, you may simplify this a little bit more, but this can also be accepted as a final answer. If you would like to do some further simplifications, feel free to do so. dh by dt can also be written as 10 over pi within parentheses 15 minus pi. You can also provide the units. This is going to be feet per minute because this is about the rate of change of height. That's our final answer for this problem. Now we will look at another example. This is your example number 3. Let's say a rocket is projected vertically upwards. Let lowercase h be the height after t seconds. You observe the rocket at a distance capital H on a level ground. Part A of this problem is obtain an equation for the distance to the rocket from the point of observation. First, we will go ahead and draw a diagram. We are going to observe a rocket launch. We are at a distance h, and somewhere here we have the launch pad, and the rocket is projected vertically upwards. Now we will assume that the rocket is somewhere here. We are going to observe the rocket from a point on the ground, somewhere here. The distance between the point of observation and the launch pad is given as capital H. Of course, capital H is going to be a constant. What changes is the height to the rocket. So the height right here is a variable. It's given as lowercase h. What we are interested is the distance between the point of observation and the rocket. Let me show that straight line distance as well. That distance is also very clearly changing. So we will let L be the distance between the point of observation and the rocket. Please note that the angle right here is equal to 90 degrees. So what should be the length L? That means the length along the green line. that should be equal to the square root of capital H squared plus lowercase h squared. As soon as you write down this equation, it's important that we understand the variables and the constants. What can you say about L? L very clearly is a variable of time. How about capital H? Capital H is the distance from the point of observation to the launch pad. That is a constant. The lowercase h is a variable. The rocket keeps going upwards, then the lowercase h keeps increasing as time goes on. Therefore, lowercase h is a variable. All right. Once these things are identified, we can go on to the next section. Part B of this problem. Find the rate of change of distance to the rocket from the point of observation. The equation that we have is L equals square root capital H squared plus simple h squared. We need to differentiate this with respect to time t. When you differentiate it with respect to time, we have identified that lowercase l and lowercase h are the variables. Now, how do you differentiate it? We need to find the rate of change of distance. That means I need to differentiate L with respect to t. When I do so, I get dl by dt on the left hand side. On the right hand side, I have to differentiate all of this. How do you differentiate that? You will need to use the power rule. On the right hand side, we have capital H squared plus simple h squared, everything raised to the 1/2 power. Then this is equal to 1/2 times capital H squared plus simple h squared, everything raised to the 1/2 minus 1 power, times you differentiate the stuff inside of that. Since capital H is a constant, the derivative of that with respect to t is going to be equal to 0. Then we just have to differentiate lowercase h squared with respect to time. First, you can differentiate that lowercase h squared with respect to h itself, and then multiply that by dh by dt, because we need to differentiate with respect to time. Then it becomes this times 2 times lowercase h, that times d lowercase h over dt. Well, this equation can be simplified some more, because I can cancel off the 2's from the denominator and the numerator respectively, and this can be simplified to become negative 1/2, and then it can be written nicely as dl over dt is now equal to, on the numerator I will just have a lowercase h, and all of this term can be written in the denominator. Then it becomes square root capital H squared plus simple h squared times dh by dt. That's basically all I need as the answer for this part of that problem. In this case, you can see we have a dl by dt, we have a dh by dt, 2 rates are given, and we have 2 other things, lowercase h and uppercase h. Basically, we have 4 things altogether in this equation. If 3 of those are given, you can find the missing piece of information. So let's do part C. What's the rate of change of distance to the rocket from the point of observation? That means I need to find dl by dt when the altitude is 100,000 feet, which means h is 100,000, and if the speed is 100 feet per second, that means dh by dt, that is the speed, that should be 100 feet per second. If the launch pad is 5,000 feet away, which means capital H is given as 5,000, you can easily substitute these values and obtain the value of dl by dt. I'm going to also introduce a part D. Here is your part D. find the rate of change of the angle of elevation. So what's the angle of elevation? Let's go back to our figure. Right here, we have the complete setup shown. Angle of elevation is right here, this angle. Let me label this angle as angle theta. How do you write down an equation for angle theta? We can write down tangent theta. Tangent theta should be equal to lowercase h divided by uppercase h. And then we can easily differentiate that equation. All right, let's go ahead and do that. Here's the equation. Tangent theta is equal to lowercase h divided by uppercase h. Once you write down this equation, what's the next step? We need to identify the variables and the constants. We know that theta is a variable. Angle of elevation increases as the rocket keeps on going up, and lowercase h is also a variable because that's the height of the rocket, and capital H is a constant because it's the distance from the point of observation to the launch pad. Now we need to find the rate of change of the angle of elevation. In order to do that, I need to differentiate this equation with respect to time t. Let's go ahead and differentiate this equation with respect to t. When I differentiate this equation on the left hand side, I will have to first differentiate it with respect to theta, and that times by d theta by dt. So let me go ahead and write down that. So what's the differentiation of tangent theta with respect to theta? That is secant squared theta. We need to times that by d theta over dt. On the right hand side, we know capital H is a constant, so I can just factor that out as 1 over capital H. And I simply have to differentiate the lowercase h with respect to time t. When you do so, it's going to be just d lowercase h by dt. Now we are done. So the rate of change of the angle of elevation is given by d theta over dt. In fact, in this problem, I need to subject that because I have to find the rate of change of the angle of elevation. When I divide both sides by secant squared theta, it will go onto the right hand side and it will be on the denominator, and secant squared theta on the denominator means on the numerator it's going to be cosine squared theta. That divided by capital H times d simple h by dt. This is the final equation I need as the answer for this problem. I will not do any numerical substitutions because those are very straightforward things. And I'm going to go ahead and stop the video at this point. If you have any questions, please feel free to let me know. Thank you so much.